Hello and welcome back to a video series on MAT 1033 Intermediate Algebra. My name is Sean Perry. This is video number 56 in the series, Final Exam Review. So I have printed off here the final exam review from the My Open Math software you've been using to do the quizzes on this course. We'll go through these questions one at a time, try them yourselves, and then I will show what the answer is after working through the problem. Question 1 says, solve the equation 7x plus 5 is equal to 3x plus 9. Enter your answer as an integer or a reduced fraction. Don't use mixed numbers. Okay, fair enough. To start with, we want to copy the problem. Next, we want to move these pieces around so that we get the x's together on one side and the stuff with no x's onto the other side. You could do this really in one move. If I'm going to move 3x over here to join the 7x, I subtract it from each side. If I want to move then the x's to the left, I should move all the not x's stuff to the right, and I can do that by getting rid of this plus 5. Minusing 5 from both sides should do that. So here I've done the same thing to both sides, and when all the dust settles, I'll get 4x from 7x minus 3x, and 4 from the 9 minus 5. To get rid of this coefficient of 4, we divide by 4 on both sides. To get rid of multiplication, you divide, and that gives us x is equal to 1. Checking our answer, we continue. Question number 2 says, solve this equation for the given variable. M divided by 2 minus 9 is equal to 1. Again, we want to start by copying the given problem. We could get rid of this dangling minus 9 by adding 9 to both sides. If I do that, I just have m over 2 is equal to 10. And then to get rid of divided by 2, we could multiply by 2 on both sides, and this gives me m is equal to 20. Alternatively, we could have gotten rid of this fraction as our first move. If I multiply on both sides by 2, being careful to distribute the 2 on the left-hand side, I get rid of all my fractions in one fell swoop. Then I have m minus 18 is equal to 2. Adding 18 to both sides, I still get 20. We check our answer and continue. Question number 3 is a much better candidate for multiplying by the greatest common denominator. If we have 1/2 minus 1/2 times x plus 1 equals to 3/8, perhaps our first move should be to get rid of all this mess of fractions. We begin by copying down the problem. We note that 2, 2, and 8 have a least common multiple of 8. If we multiply it by that on both sides, it will have the effect of canceling every fraction. On the right-hand side, you can see multiplying by 8 cancels straight away. On the left-hand side, we need to distribute, and 1/2 of 8 is 4. Now we can proceed to solve this in the normal way. If we minus 4 from both sides, say, we then get negative 4x plus 1 is equal to minus 1. Divide both sides by minus 4. And we're going to wind up with x plus 1 is equal to a fourth. I can then subtract 1 from both sides, and simplifying this fraction, just remember how to get like bases, and we'll see that that's going to have to be negative 3/4. That isn't to say that we had to get rid of the fractions. We could have stayed and played with fractions right here, minusing 1/2 from each side. We would then have to, though, do this fraction subtraction right here, getting like bases and taking a difference. We would wind up with 1/8, negative 1/8. And now to get rid of this 1/2, multiplying by the reciprocal on both sides, we still wind up with that equation x plus 1 is equal to a fourth. We would solve this the same way as we did originally and wind up getting the same answer as we did before with negative 3/4. We check our answer and move on. Question number 4 asks us to solve the following equation. It's a linear equation, so we'll solve it the same way as we did with the first problem. The first thing we should do is get rid of these parentheses so we can group our like terms. Distributing the 6 against each of those gives me 6x plus 24 minus 8x minus 2x minus 24. This gives me some like terms on the left-hand side that I can combine and get minus 2x plus 24. Now we can solve it. Well, let's take a quick look here. I mean, we should already notice that the left and right-hand side are the same, right? So if we were to do the same thing on both sides, trying to cancel, we would wind up canceling everything and winding up with 0 equals 0. This is a tautology, or a statement which is always true no matter what. And that means that it doesn't really matter what x you put in here. The left-hand side and the right-hand side are always going to be equal. We could say this is the real numbers, all reals, any number, negative infinity to positive infinity, and so on. I'd just like to note that whenever we write equality statements, there's always one of 3 options at play. We can write at the end of solving an equation this conditional statement, x is equal to 2. This is sometimes true, namely it's true if and only if x is equal to 2. We have statements like x is equal to x or 0 is equal to 0. These statements are always true and indicate the answer is all real numbers. And finally, when solving equations, you might wind up with this, a contradiction. 0 is equal to 2. No, it's not. 0 is never equal to 2. And so this is not a true statement. That means that no x's would have sufficed to solve the equation. Checking our answer, this is indeed what they were looking for in set notation, and we move on. Question number 5 asks us to solve the following inequality. They want it graphed, and they want the solution in interval notation. As usual, the first thing we want to do is copy the problem carefully. Then we're going to want to solve this as if it were a linear equation and not an inequality, keeping in mind that if we ever multiply or divide by a negative number, we need to flip the direction of the inequality. But to begin with, we distribute. This gets us the following terms. Then we want to combine like terms. There's some like numbers on the left-hand side. There's some like x's on the right. Combining those, we get minus 6x minus 2 is less than minus 5x plus 2. Now, there's always going to be a direction you can move things to keep your coefficients of x positive. So I'm going to move this 6 from this side to the other, from left to right. And that means I'm going to move the numbers from right to left by minusing 2 on both sides. These cancel or reinforce as such. We wind up with 1x, which is just x, is greater than or equal to minus 4, or minus 4 is less than or equal to x. However you want to say it, it's the same thing. Now, for this, we would use a closed circle because this is inclusive inequality. It includes minus 4 as its edge case. And we want all the x's greater than that, so we shade on this side. To write that in interval notation, we use a bracket to indicate that we have included the minus 4. We go all the way up to infinity as an upper bound, but we don't include the infinities, so we use a parentheses. Let's check our work. Looks good. I accidentally forgot to load the answer for the graph, so we'll just have to go by this interval here. The graph would, of course, look like a filled-in 4, and then everything shaded on this side, an arrow this way to indicate we're going all the way up to infinity. All right, let's look at problem 6. Problem 6 is a inequality with some fractions in it. We start by copying over the question, and we could subtract on both sides by 4 over 2, but 4 over 2 is just 2. Let's reduce this fraction first. Now, minusing 2 on both sides, we will wind up with 15 over 8 minus 2. We're going to have to get that in like bases before we can subtract this fraction one from another. So multiplying on the top and bottom by 8, we get 16 over 8. And this indifference gives us b is less than negative 1/8. That means we're going all the way up from the lowest possible numbers up to negative 1/8, and then we don't include it because this is strict inequality. It doesn't include its edge case. Another way we could have approached the problem is to clear denominators first. That's sometimes a good way of starting things with fraction problems. If I multiply on both sides by 8, it's going to cancel completely from the right-hand side, and on the left-hand side, it will cancel by distributing. 2 goes into 8 4 times, so we'll get a 4 times 4 here, and then we'll also wind up with an 8 times our b. 4 times 4 is 16. Minusing 16 from both sides, I get minus 1, and dividing by 8, I get negative 1/8. So same as before, we wind up with the same solution. Notice that we don't flip an inequality if we divide a negative, only if we divide by a negative. And checking our work, we move on. Question 7 is another linear inequality. We begin by copying the problem. And just like any other linear equality, we would want to distribute first to simplify each side. Negative 4 distributes as such. And now I have chosen to move the x values so that I do get a negative coefficient because I want to remind everyone about what happens to our inequality in that case. So if we add 15x to both sides, we will move the x's from the right over to the left. But that means we want to take the numbers and move them from left over to the right by minusing 24. If I do that, I wind up with 13x. Negative 13x is greater than negative 22. So we divide by negative 13, and that dividing by a negative is what tells us to flip the direction of this inequality. The negative over a negative is still positive, and this doesn't reduce. So since x must be less than this number, we go from negative infinity up to this number, 22 over 13, and we use a parenthesis to show that we're not including that because this is strict inequality. Checking our work, it looks good. Question 8 asks us to solve for the specified variable. They say I is equal to what if S is equal to P plus I? This one goes pretty quickly. To isolate I, we need to get rid of P. It's a positive P that we're adding here, so we minus P from both sides to get rid of it. Subtraction cancels this addition that's going on here. And that gives us S minus P is equal to I. We are solved for I because I is alone on one side of the equal sign. And that is our answer. Question 9 asks us to solve this rational expression, this quotient expression for x. X cannot be on the bottom of a fraction and consider it solved for because something else is still going on involving the x. It is not alone if it's in the bottom of a fraction. And so after we copy the problem, our first move should be to get x off of the bottom of that fraction. We multiply on both sides by the term 10 minus x, and that has the effect of canceling it on this side, as long as, of course, x was not equal to 10, in which case this would be 0 over 0 and undefined. But we multiply still by the denominator 10 minus x, and that clears it on the right-hand side. And on the left-hand side, I now want to isolate this x. I can't do it while he's stuck in this parentheses, so I distribute my y. Once I do that, I can see that I have a x term and a not x term. I start by moving the not x term to the other side. We are adding it, technically. This is plus negative xy, but this is a plus 10xy. So we minus 10y from both sides to turn this into a 0 and isolate our negative xy. Now, to get rid of the negative sign and the y in one fell swoop, we could divide by negative y on both sides. The negatives cancel, and we wind up with x is equal to 6 minus 10y over negative y. This is a fine place to leave it, but we can actually do a little bit better. We can get rid of this minus symbol by reversing the order of subtraction. Reversing the order of subtraction would pull out a negative 1 here, and that would cancel with the negative 1 on the bottom. And so we could really write this most simply as 10y minus 6 over y. Checking our answer, that is indeed the form that they wanted it in. Question number 10 says, first for this equation, complete this table, and then they're going to want a graph. To complete the table, we first copy down the rules, and then we're going to substitute the following values in for x. Notice when we substitute in negative 2, we wind up with negative 2 over 2. That simplifies to negative 1. Negative 1 is positive 1, and so when we add those together, we get 3. Likewise, if I substitute in 0, this whole term goes to 0, and adding 2, I just get 2. Finally, they want us to substitute in 2 for x. If I do that, I wind up with negative 1 in this position here, and adding it to 2, I just get 1. If we plot those points, x is minus 2, y is 3, x is 0, y is 2, x is 2, y is 1, we get the following 3 points, and connecting them to show it happens in the in-between, we get this line. That is indeed what they got as an answer for the graph. Here I've shaded the points to show you how that lined up with what you see on the table, but we should still check our answer in the table, and it's indeed what we got with our substitution. Moving on. Question 11 is similar. It asks for a table to be complete and a graph to be constructed. Again, the notion is to write down your equation, substitute in the given values for x, and evaluate. If I plug in negative 1 here, we get 3 times negative 1, which is minus 3, and adding that to 6, we get 3. Likewise, if I substitute in 0, I wind up with 0 plus 6, which is 6. And if I substitute in 1, we wind up with 3 times 1 plus 6, that's 3 plus 6, that's 9. So we could plot these points. Here I've graphed those 3 points, minus 1, 3, 0, 6, and 1, 9. And this would be an example of our graph. We check our answer for the table and for the graph. Looks good. You can see I've put dots where our points were, so you can see how the table lined up with the graph. Moving on to question 12. Question 12 gives another table. We're asked to fill this out and construct a graph. One of the easiest ways to proceed, since we're given all x's to substitute in, is to first solve for y as a function of x. To do this, we add 3x to both sides, and then we divide by minus 2, remembering to distribute that into both terms here. We get y is equal to minus 3 halves x minus 4. Now we're going to substitute in negative 2, 0, and 2. So we do that here. Minus 2 cancels, gives us positive 3, and then minusing 4 from that we get negative 1. Substituting in 0, we would wind up with 0 minus 4, and that's negative 4. Substituting in 2, they would cancel the 1, and we would get minus 3 minus 4, which is negative 7. And that completes our table. We then plot those points, which would look like this. And using that, we can match the graph that they're looking for. Here is the graph, and here you can see the points plotted from the table. Checking our table values, everything looks good, right? So we can move on. Question number 13 asks for us to match this equation here to one of these four graphs given. Since the graph is in slope-intercept form, it's easy to pull out the slope and the y-intercept. The slope is the coefficient of the x. It's minus 2. So this is minus 2 over 1. This tells us that when we go to the right by 1 unit, we're going to go down by 1 unit. And the minus 3 tells us the value that y has when x is 0. When x is 0, y has a value of negative 3. That's why it's the y-intercept. From here, we follow the slope to go over by 1 to the right, and since it's negative, down by 2. And that brings us to a second point. 2 points is all we need to determine a line. Using this, we could match the graph that also has a negative y-intercept and a negative slope, which is indeed the answer. Moving on, question 14 concerns the domain and range of this graph. The graph seems like a part of a curve, a finite curve. It starts here, it goes up, it goes down, and it ends here. The filled-in dot indicates this point is included in the graph, and this open dot indicates that this point, 3, negative 5, is not included in the graph. Another important point to note is that when you see this crest, this peak that it does here, this point of the peak, 0, 4, this is going to be included. That's going to be an important consideration. To find the domain, we ask what x values were used to make this graph. Everything on this graph has an x and a y value. The total set of x values used gives us our domain. We use every x value from negative 1 and including negative 1, which is this point here at negative 1, 3. And we use all of these x values. Every single point here corresponds to some x value between negative 1 and positive 3, except this one here at 3 minus 5, it doesn't get included. And so there really wasn't a point used for x is equal to 3. That's why we want to leave it out. So we use an open circle to show that here. The interval that corresponds to that set is bracket negative 1 up to 3 parentheses to show inclusion and exclusion respectively. The range goes somewhat similar. All of these are y values that get used. So we look at every point on this curve and we look left or right to decide which y values we're going to include. Now, we also need to include this crest point at 0, 4. The value 4 is a y value which is attained by the graph. That means we're going to use all of these y values, starting from this lowest one, which corresponds to this open circle here. So we leave out minus 5, but we include everything else all the way up to 4, the highest y value that is used. And that inclusion means we use a bracket with the 4, and the open circle is why we use a parenthesis with the minus 5. So these are our two intervals, and we can check that those are correct. Look pretty good. We move on. Problem number 15 says, find the domain and range of this graph. Now here, this is really, I don't like this example too much because, well, I mean, you have to know a little bit about what behavior they're expecting you to see of this very tiny segment of a graph. So let me try to break down what they want you to see here and how you should respond. First off, we need to note that we are going to include this particular point. It is both our highest y value and our highest x value. All the used x values and used y values are smaller than this point, which is at negative 2, 2. Now, because this seems to keep going forever, because this arrow points us out, it doesn't end, it just keeps on going, we are going to say that the x values used are all the ones all the way down. So our domain is going to be from the lowest possible point, negative infinity, all the way up to this last point that gets used, minus 2, and we include it with a bracket because this circle is filled in. Our range is somewhat more complicated. The reason being is that we actually are sort of required to see that this looks somewhat like a sideways parabola, and that it's not actually an asymptote. It's not hugging the x-axis. It may be getting shallower and shallower, but it actually is going to keep going. It's going to keep getting wider and wider. We should contrast that with something that does start to hug the x-axis, where it seems to get there, and then sort of maintain its distance a little bit, right? It might be getting closer and closer, but the rate at which it is slowing way, way down. This one we're supposed to infer, and again, this is why I don't particularly like this example, that this actually keeps widening. Even as it shallows, it will eventually hit every single y value going down, and that's why we're going to use this minus infinity up to the largest y value of 2. So keep in mind, if it looks a little bit like a parabola, like the graph of x squared or the square root of x, in this case, you're going to want to infer that it keeps widening and that you should keep going down as this gets farther and farther to the left in this case. Some graphs like 1 over x have asymptotic behavior, where they get closer and closer to something without ever crossing it. This might be a segment of a rational function, and it never crosses my x-axis. So without crossing, I might infer that this has a range only from 0 up to 2 and without including it. But ours is going to, I think, be the parabolic one. Let's check. And checking our answer, it is indeed going from negative infinity up to 2 in the y direction. Again, really don't think this is a super fair question. Very hard to see that this isn't asymptotic behavior here, that it will cross the x-axis and every line underneath that. So, but that's the lay of the land. Keep that in mind as you go through these questions, that if it sort of looks like a parabola, it's going to keep widening forever, and that affects the range in this way. All right, moving on, question number 16 says, find the domain and range of this graph. Now, this is, again, another thing that looks like a sideways parabola, right? This, when I said parabolic behavior earlier, this is what I was talking about. It's getting shallower and shallower. The slopes are getting less and less steep as we go to the left here, but it's not actually ever going to level off. When a function has that kind of behavior, when it looks like this parabola, and we should note a couple points on the parabola. Notice that it has this sort of peak, so to speak, a sideways peak here at this point. Then it goes up 1 over 1, then up 1 over 3, and then up 1 over 5, actually, even though you can't really see it. That's sort of a hallmark of parabolic behavior, is that we're getting, a shallower and shallower graph here. But not to put too fine a point on it, what are they asking for? They're asking for their domain and range. Now, the domain is easy to get. These arrows tell us that it keeps on going to the left and that its highest point is this 3. We include the point at the vertex, at the sort of peak here going to the side. So this is going to have the domain of negative infinity up to 3 bracket to show that we are including that point. Now, the range, on the other hand, is again a little bit more complicated. You need to know this little piece of lore, that parabolas keep widening forever. They get wider and wider and wider. And so eventually every y value is going to get hit, and the range goes from negative infinity to positive infinity. To answer their question about is this a function or not, we need to simply look at any vertical line that hits it in more than one place. If there is such a line, if it gets hit by any vertical line in more than one place on this curve, it's a relation but not a function. Functions only have one y value output for every x value input. Clearly, this one does not, so this is not a function. Checking our work, we see that is indeed what they were looking for the domain and range. As well, this fails the vertical line test and is not a function. Moving on, question 17 says, here is a function. It has an input of x and asks you to do the following things with it. Square it, times it by 7, add that to 6 times it, and then minus 7 from that. And they want to know what would happen if you plugged in for x the values of 0, of 2, of minus 2, and the expressions x plus 1 and negative x. So say, for example, if I plugged in 0 as the first question asks, then every x is replaced with 0. 0 squared is 0 times 7 is 0, 6 times 0 is 0, and so all we wind up with left is minus 7. On the other hand, if I plug in 2, we're going to need to follow our PEMDAS rules and do this appropriately. We begin by squaring, which gives us 4. Then we take care of any multiplication or division that's left. 7 times 4 is 28, 6 times 2 is 12, minus 7, we get 33. Same with negative 2. We should keep in mind that negative 2 itself is being squared and squared first, so this gives us positive 4. And then taking our products, we now wind up with negative 12 instead, and doing the rest of the arithmetic, we get 9. Let's look at the one with an expression. If I square this, well, let's just keep in mind how to square such an expression, right? We would need to write it as times itself and FOIL. You wouldn't be able to just square each term, that's a big no-no. But writing it next to itself and distributing twice, we wind up with x squared plus x, that's plus 2x, and plus 1 for the last term. That's what we get when we square x plus 1. Now we want to multiply that by 7. We get 7x squared plus 14x plus 7, and distributing the 6, we get 6x plus 6, and there's still this dangling minus 7 there. Now we want to combine like terms. So like terms have the same letter and the same exponent. There are no other x's squared, so we're going to leave that. But there is a 14x and a 6x. I can combine those to get 20x. And there is a 7, a minus 7, that's 0, and so we just have this plus 6 remaining. Finally, what happens if you put a negative x in here? Well, negative x squared is positive x squared. And this minus sign in here could be brought out front, so we would just get minus 6x. Minus 7, I don't have anything really to do with that. This is our final answer because they're all unlike terms. We cannot simplify it any further. We check our work by checking these answers, and the saga continues. Question 18 asks us to find the slope of two lines. And then they want us to ask whether or not these are parallel, perpendicular, or neither. To do this, let's copy these points over. The first point, which I'll call x1, y1, is minus 3, minus 2. And then in the line 1, this is also for x2, y2, we get negative 6 and 7. Likewise, with line 2, we have the first point, 6, 16, and the second point, negative 3, 1. We need to know the following things about slopes. We need to know how to calculate them from 2 points, which is you take the difference of their y values and divide by the difference of their x values. This needs to be done pairwise in the sense that these 2's line up, these 1's line up, although it doesn't actually matter if you do y1 minus y2, but you'd have to do x1 minus x2 to balance. A perpendicular slope, which is what this symbol here means, is the negative reciprocal of a given slope. So flip it and change the sign. And a parallel slope, which is what this symbol means, is simply equal to a given slope. So if we find that we have a negative reciprocal between these two slopes that we're about to calculate, we will have found a perpendicular line. And if we find that the slopes are equal, we will have parallel lines, and they are neither in every other case. So we carry out these calculations, right? We do minus 7 minus minus 2, that's negative 5. Minus 6 minus minus 3, that's plus 3, so this is minus 3 in total. And the negatives cancel to give me 5/3. Likewise, 1 minus 16 is minus 15. Negative 3 minus 6 is negative 9. And simplifying by dividing 3 from each term, we get 5/3. Positive. So these are equal to one another. The slope of line 1 is equal to the slope of line 2, and so they are parallel. If one of them had been 5/3 and the other had been negative 3/5, that would have been perpendicular. And if they were unequal in any other way, they would have been neither. Checking our work by looking at these answers, we move on. Question 19 says, find the equation in y equals mx plus b form, slope-intercept form, that has a slope of 5 and passes through the point 528. The simplest way of proceeding from here is to use the form of a line called point-slope form. You can see by dividing x minus x1 to the other side, we would simply have the definition of slope. But here, we've been given a slope and given a point, and we can substitute it into these places and then solve for y to get it in the proper form. Plugging in our 5 and 28 for x and y, respectively, we distribute the 5 against both terms, and then solving for y means adding 28 to both sides. Once we do that, we wind up with a positive 3 here and a 5 for our slope. So our slope-intercept form is y equals 5x plus 3 as such. Question number 20 is similar. It asks for the equation of a line that has slope of 1/2 and passes through 6, 4. Again, we will rely on point-slope form. Y minus y1 equals m times x minus x1. Substituting in these values, we distribute the 1/2 slope, which gives us 1/2 x minus 3, and bringing over our 4 to solve for y, we have y is equal to 1/2 x plus 1. Here you can see that they didn't give any particular form of the equation that we needed, so they would have accepted this unsimplified version as well. But if we're going to go all this way, why not just get it in an appropriate form? Here it is in y-intercept form, slope-intercept form. Moving on, question 21. They ask for this to be written in standard form. It's given in no particular form. We have y's, we have x's, nothing's really, solved for. Let's see what we should do here. Standard form has certain requirements. Standard form says that you want it to be ax plus by equals c, and these should be whole numbers if possible, and a should be greater than or equal to 0, right? Maybe it's equal to 0 and you wind up with some kind of horizontal line, but for the most part, this should be a positive number. Now, to begin with, let's bring the x and y together on one side, and the numbers, as you can see, c is just a number here, we want to move those over to the right. So I add 6x to both sides, I move this minus 9 by adding 9 to both sides, and when all the dust settles, we have 6x plus 1y is equal to 9. If you have just a y, that's 1y. So, are we good? We're good. They're all whole numbers, and the a term, the x coefficient, is positive. So this is done. Checking our work, we move on. Okay. So question 22 is going to start to get into these questions involving the simplification of exponents. It says write this using a positive exponent. Be sure your variable matches that which is in the question, and write it in simplified radical notation as well. In order to simplify this exponent, what we're going to need to remember is that a power raised to a power is the product of powers. And so z to the power of 1/5 to the power of 1/3 is z to the power of 1/5 times 1/3. Now, 1/5 times 1/3, multiplying fractions top to top, bottom to bottom, this is 1/15. And to finish the problem, we need to note that a fractional power is exactly what a radical is. A to the b over c is a to the b with a cth root taken of that. So we put a c in this index notational spot right here. This position is called the index, and that's the denominator of your fraction. Now here, my numerator was 1, my denominator is 15, so this is the 15th root of z to the 1, which you can really just write as the 15th root of z if you like. Anything to the first power is itself. Let's check our answers. Looks good. They even put z to the 1. Kind of goofy, but whatever. We continue. Question 23 says, simplify this expression, x to the 2/3 over x to the 2/5. To do this, the primary thing we need to know is that the quotient of powers is the quotients of bases, the quotient of like bases is the difference of their powers. So that means to solve this, to simplify this, we need to know how to minus 2/5 from 2/3. So I've put that over here. Remember, you need to get like bases. That's 10/15, multiplying this one by 5 over 5, minus 6/15, multiplying this one by 3 over 3. Once we have like bases, we just subtract the numerators, and that's 4/15. So this simplifies to be 4/15 in my exponent. Checking our answer, we see that is correct. Moving on to question 24, it says simplify the following. It's a product of like bases. In order to simplify this one, we need to recall that the product of like bases is the sum of their exponents. So we are being asked to add 1/3 and 1/5. How do you add a third and a fifth? You need to unsimplify a third. Multiplying by 5 over 5 gives you 5/15. Multiplying this one, 1/5, by 3 over 3 gives me 3/15. And now, and only now that you've gotten it in terms of 15ths, can we just add the numerators to get 8/15. So the product of these two powers turns out to be x to the 8/15. Checking our answer, looks good. Moving on to question 25, we are now asked to simplify this sum of radicals. They want our answer stated exactly, which means in terms of radicals, no decimals. You put a decimal in here, it's not going to mark it correct. So first, copying the problem over, what we're going to do is simplify each one of these radicals. Now, this last one, 2 radical 3, is too simple to simplify. It's already in its simplest state, but these others can be reduced. So let's go over reducing radicals again. I think the best way to reduce radicals is using factor trees so that we can see when we have squares that we could take the square root of. Or if we were dealing with higher powers, we might want to look for 3 of a kind or 4 of a kind. This is much more easily done once we see all the prime factors of a number. So here, notice I've taken 180, I split it into 18 and 10, 9 and 2 is how 18 multiplies, 9 is 3 times 3, and 10 is 2 times 5. So 180 is 3 times 3 times 2 times 2 times 5. From here, we can easily see what squares it has. It has a pair of 2's, it has a pair of 3's. And 4 times 9, that's 36, which is a square. The square root of 36 is 6. So rewriting 180 as 36 times 5, I could take the square root of each and get 6 radical 5. Likewise, you could also go straight from here and pull out any pairs you saw as that number. We're pulling out pairs because this is a square root. 3 times 3, if I take the square root of that, it's just 3. And we're allowed to distribute radicals and exponents in general around products. So that leaves just a 5 stuck inside the radical and a 3 and a 2 that come out. However you see it is fine. This is 6 radical 5. The square root of 180 is just 6 radical 5. Same thing with 147. If we break this up, we can see that a 3 could come out and a 49 remains. If we write that, 49 is a square, so if we write the square root of 147 as the square root of 49 times 3, we're really just taking the square root of each part here, and the square root of 49 reduces to 7. So the square root of 147 is 7 radical 3. Likewise, 20 splits into 4 and 5. 4 is a pair of 2's, and so we could take a single 2 out. Or, seeing 4 as a square, we could write the square root of 20 as the square root of 4 times the square root of 5, or the square root of 4 times the square root of 5, which is 2 times the square root of 5. However you simplify this for yourself is fine, but the idea is that because we're looking at square roots, we are pulling out pairs of numbers, or perfect squares, whenever we see them. Now, let's take these simplifications and bring them back to our problem. If we rewrite the square root of 180 as 6 radical 5, we have negative 5 times that, and likewise this becomes 7 radical 3 times 5, and 2 radical 5 times 4, and our little lone negative 2 square roots of 3. Now, grouping the numbers here, we have minus 30, we have 35, we have 8, and now we look for like terms in the sense of having the same base and the same fractional power of square root, 1/2 power. So where do we see that? We have 5 square roots and 5 square roots here, and 8 of these things minus 30 of these things is minus 22 of these things, called square roots of 5. Square root of 3 and a square root of 3 likewise can simplify. You can factor that out, combine the coefficients. That's like terms, baby. So this is 32 square roots of 3. We check our work. This is indeed correct, and we continue. So question number 26 is similar. Pause the video, try it for yourself, and then we will give it a shot. What we first want to do for 26 is to simplify each one of these radicals. The square root of 5 does not simplify, but each of these other ones has a square hidden amongst its factors. Here's my work to simplify the radicals. 252 is 2 times 126, which is 2 times 63, which is 9 times 7, and 9 breaks up into 3 and 3. So again, we have 2 2's and 2 3's. We can pull a 6 out. What remains? A 7. So square root of 252 turns into 6 square roots of 7. 45 is 9 times 5. We could pull out a single 3 from that. The square root of 45 turns into the square root of 9 times the square root of 5, which is 3 radical 5. 28, very similar. It's a perfect square, 4 times 7. And so we can rewrite the square root of 28 as the square root of 4, 2, times the square root of 7, which remains inside the radical. If we fill these back into the expression, we have the following. 1 times 6 is 6, negative 5 times 3 is negative 15 square roots of 5, and this is 10 square roots of 7 minus 4 radical 5. Now, our radical 5s are here and here. We could group them together. Minus 15 and minus 4 are the coefficients. We can group our square roots of 7 in the same way. 10 plus 6 give me 16 radical 7, and minus 15 minus 4 gives me minus 19 radical 5. Is that correct? You better believe it. On to question 27. 27 is a product of two radical expressions. Actually, it looks very suspicious because we have matching in all places except for here where we have two different signs. This is going to look like a difference of squares formula, and we're going to see a lot of cancellation in the radicals. So here's my work for 27. Let's see how it goes. I've written it in a slightly different form than the usual foiling because I want you to see that some of these things are going to have square roots times themselves, which is to say squaring them, and that cancels. Other ones are going to have a mixture of radical 3 and radical 7. But because of the difference of signs here, we're actually going to get cancellation as well. So for example, because we have two square roots of 7 here, 4 times 4 is 16, but radical 7 times radical 7 is just 7. And 5 times 5 is 25. Radical 3 times radical 3, or radical 3 squared, is just regular old 3. On the other hand, 4 times 5 is 20. Radical 3 times radical 7 is radical 21, but this one turns into negative 20 radical 21, and so a positive minus itself goes to 0. Now we just finish up the arithmetic here. 16 times 7 is 112, 25 times 3 is 75, and their difference is 37, our final answer. As such, moving on to number 28, we have the following. It wants your answer exactly, meaning in terms of radicals. And really all that's being asked here is for you to distribute the square root of 5. There is another square root of 5, and so we wind up with a square root of 5 squared, which cancels to 5. A square of a square root gives you back its argument. And it adheres to this minus 4. There's nothing really we can do to simplify that. All that we can really do here is simplify the 6 times 5 into a 30. We could rewrite it this way. I believe either way is acceptable. Addition is commutative after all. Checking our work, that is the case. They left things in this order. I kind of like the other order with the 30 in front because then you get one fewer symbol, but hey, who's counting? 29 says, multiply these out, okay? So that's going to require some foiling, but that's really all it's going to require. We have a square root of x times a square root of x. That's the square root of x squared. We just get x. We have minus 1 times 6. That's minus 6. And for our middle terms here, we have minus 1 times square root of x. We have square root of x times 6. That's 6 square roots of x. Combining these as they are indeed like terms, we have minus 1 and 6. So this gives us positive 5 square roots of x, and we're done. Checking our work, we see that's all they want. Moving on to question 30, our halfway point. So question 30 is a complex multiplication problem. It asks us to multiply these two complex numbers together. This is really just going to be a process of foiling and keeping in mind that the square root of I squared, is minus 1. When we multiply these out, we have first terms, we have inner, outer, and last terms. We wind up with the following. I've grouped them like this because this is 15i times 3i giving me 15i squared, that's going to pull a minus 1 out, and it's not going to be complex valued for this part at all. We're just going to get a minus 15 away from 40. That gives me 25. On the other hand, 5i times 10 is 50i. 4 times 3i is 12i. And writing these in like terms of I, we get 62i. So 25 plus 62i is our final answer. And there we have it. Question 31 looks very similar to the one we looked at with radicals, where we have matching in all places except two different signs. This is going to be reminiscent of the difference of squares formula, and as such, we're going to get rid of all of our complex values. Let's see how that looks. So again, we're just foiling here. We foil, we get a 4. We foil the last terms, we get a minus I squared, but that's minus minus 1, which is just plus 1. And the middle terms, we're going to have 2i, but we're also going to have minus 2i. And a number minus itself, even if they're complex, is still 0. So this goes away entirely. We have no imaginary terms. We just have the 4 plus 1, and so our answer is 5. We call being different in just this sign of the imaginary part being conjugates in complex numbers. And this will always, if you multiply a complex number by its conjugate, give you a simple real number. All right, moving on to 32, we are asked to look at this through the lens of synthetic division. Synthetic division is a shortcut of polynomial long division used when we have a very simple linear term as our divisor. There are 3 parts in doing synthetic division. First, we must encode some numbers then we perform an algorithm, then we decode the answer. The way that we encode the numbers is first by looking at what is the root, what is the 0 of the denominator. The denominator will be 0, x minus 5 will be 0 when x is equal to positive 5. This number goes in this little box here. We then set up the rest of the numbers in blue by looking at the coefficients of the dividend, the number being the polynomial being divided. This is 2x cubed minus 5x squared minus 23x minus 7. So we put the 2, the minus 5, the negative 23, and the negative 7 along the top. The algorithm begins by dropping this first number straight down, just copying it down. And then we proceed as follows. We multiply 5 by 2 to get 10. We put that here and we take their sum. Negative 5 plus 10 is 5. Then we repeat. We multiply the 5 by the 5, we get 25. We take their sum, we get 2. And we repeat. We take 5 times this 2, we get 10. We take their sum, and that is a positive 3. We've reached the end, so we stop. Now we have these numbers as an output from our algorithm, 2, 5, 2, and 3. Now we have to decode what those mean. If we started with a cube, we're going to drop down 1 degree to a square. And so we have 2x squared. These are going to be the coefficients of a polynomial. 2x squared, 5x plus 2, and this last term is our remainder. To write this in quotient plus remainder form, right, we can write the dividend divided by a divisor as equal to a quotient plus the remainder over the divisor still. So we write that 3 here, we put it over the x minus 5 still, and our quotient polynomial goes out front. This is very reminiscent of a mixed number when you had an improper fraction and you wrote it as a whole number part plus a proper fraction. We check our work and it looks pretty good. Let's go on to the next one. It's another synthetic division problem. Question number 33 says, what do you get when you divide this by x minus 5? Would have liked it if they chose a different divisor, but whatever. So to begin with, right, we establish our root. Our root of x minus 5 is x equal to 5. This is the x value, which would make this term equal to 0. We put that here. Then we have coefficients of 1, 5, negative 44, and negative 34. Dropping the first one down, we begin our algorithm. 5 times 1 is 5, plus 5 is 10. 5 times 10 is 50, plus negative 44 is 6. 5 times 6 is 30, plus negative 34 is negative 4. And we've reached the end. That's our algorithm. So now we decode the results. This drops from an x to the third to an x squared. So we wind up with 1x squared plus 10x plus 6, remainder minus 4. And so that's our polynomial part, our quotient, at minus the remainder, so minus 4, giving us minus 4 over x minus 5. Checking our work, that is in fact the case. Now, I'm not incredibly satisfied with the examples that they gave you for synthetic division, so I want to offer one more that isn't on this page. That's because one of the most common mistakes with synthetic division is to forget a zeroed coefficient. Notice this one, x cubed minus x plus 1, has no x squared coefficient. You cannot forget that any more than you could forget the 0 in 1024 divided by 4. You have to have that or it doesn't work. So this 0 must get copied down. We could establish the root of this is minus 1. Dropping our first coefficient down, we take a product, then a sum, then a product, then a sum, then a product, then a sum to reach the end of our algorithm. This would then give me x squared minus x plus 0 plus 1 over x plus 1. Our next questions are more about the simplification of powers. Let's look at number 34. To do number 34, we have to keep in mind certain rules, which I've written to the side here. We can perform these problems in many different orders. So if you want to do it in a different order, if you want to distribute this minus 2 to every term first, that's great. But we do have to keep in mind what those numbers are and what they're doing relative to each other. Here, for example, I've started by simplifying the r's. We have r to the 5, or 5 r's in product on top, and 3 r's in product, or r to the 3 on the bottom. That quotient of like bases gives me a difference of their powers, and 5 minus 3 is 2. There's nothing else I can really simplify here, so I could either distribute this to the power of minus 2 to each term. I like to think about it in 2 separate steps. what does the negative sign up here mean? It means a reciprocal. So I like to get rid of that negative sign and flip the fraction as its own step. Something to the -1 power is its reciprocal. And then I could distribute the 2 freely to each term. 2 to the 2 is 4, same with the r to the 2 to the 2. And then 5 to the 2, we wind up with 5 squared, that's of course 25. And so this is our final form. As such, checking our work, we see that looks good. Let's move on to question 35. Simplify this expression completely. We got a to the -3 times b to the 8 to the power of -2. So we're not going to be able to combine the a and the b at all. So we're going to want to take advantage of the fact that exponents distribute around multiplication and division for that matter. And we're going to want to then hit each one of these, a to the -3 and b to the 8, with power to a power, which is the product of powers. If we do that, we have -3 times -2, that's +6, and +8 times -2, that's -16. To write this with positive exponents, we just need to move any negative exponents that are sort of in the numerator, this is over 1, down to a denominator. If there were any that were in the denominator and were negative, we'd move them to the numerator. But that's it, and then this is written with positive exponents. Let's check our answer here. Looks good. Moving on to question 36, we now want to take this x to the -5 to the 8, put that over x to the 2 to the -9. So we need to take care of this power to a power thing first before we can take care of the quotient. That's essentially order of operations. Again, power to a power is the product of powers. So -5 times 8, that's -40. 2 times -9, that's 18. And now, as we saw, the quotient of like bases is the difference of those powers. And minusing -18 gives me a total of -22. We slide that to the bottom as a +22, and we're done. As such, okay? Question 37 is our first polynomial. We have x squared plus 10x plus 16 equals 0, solving for x. Now, we could use the quadratic equation. I would strongly advise against using the quadratic equation if factoring will work. It's way easier, way faster to learn how to factor instead of taking the time to plug this into the quadratic equation here. So we set up parentheses. We drop a plus into each position, right? We drop a plus down and say a plus times what is another plus when we FOIL, and that's going to require 2 positive signs here. Factors of the final term, 16 and 1, 8 and 2, 4 and 4, and which of those give us a same sign sum of 10, 8 and 2 do. So we put an 8 here, we put a 2 here, and then we use the zero product property to write this as 2 simpler equations. That's why we're factoring, because now we can say our two answers are where 8 plus x is equal to 0, which is at -8, or where 2 plus x is equal to 0, which is at -2. So these are our 2 answers. There we have it. On to the next one. 38 says we want answers for the equation m squared minus 12m equals 0. Again, this is another situation where we're really going to want to factor and not try to use the quadratic equation. So how's that going to look? We're going to be able to take a greatest common factor out. Remember, that's always your first step, is to see if you can take a greatest common factor out of every term. In this case, there's an m in each term, so we can divide that to the front, rewrite this as m times m minus 12, FOIL it back in if you want to make sure that that is the correct factored form. And now setting each factor equal to 0, we have either m itself is equal to 0 or m is equal to positive 12. Remember, we have to set this term equal to 0 and solve, which changes the sign here. If there was another term in front of a, that would also make this a fraction. But in this case, we just get m is 12 and m is 0 as such. Question 39 is a word problem asking us to figure out the remaining side of this laptop screen whose diagonal is 14 and whose height is 7 inches. You might recognize this as a right angle problem. You need to memorize the Pythagorean theorem, which says that if I have legs of a triangle A and B, a right triangle, and C, the leg opposite from that, the hypotenuse, then we have the following relationship, that a squared plus b squared is equal to c squared. In this situation, 14 is playing the role of the hypotenuse, and these two can be a or b, whichever you like, but it's mandatory which one is c. It's got to be the one across from the 90-degree angle. So plugging in our unknowns here, we have one unknown, which is this lower leg. And we also have 7, which we knew as being the height. So what we have once we evaluate the squares is that 49 plus b squared is equal to 196. Subtracting 49, we get 47 is equal to b squared. And that means that the square root of 147 must be b. Normally we'd have a plus or a minus here, but since we're talking about lengths, it can't be negative. We don't have negative lengths, so we can just select the positive square root, the principal root here. How does 147 square rooted simplify if you wanted that? Well, it's actually 49 times 3. We saw that in a previous problem. And that's 49 square rooted, that's just 7. So we could simplify this to write it exactly. It's actually the decimal form is 12.124 and so on. And rounding that down, because this is less than 5 in this position here, to 2 decimal places, it's 12.12. It asks us to round to 2 decimal places. However, the answer is given to far more. I don't know why that is, but you can see that it is in the first 2 places 12.12. Okay, let's go on to 40. 40 is another right-angled problem. It says, I want you to find this now. So here we have x, the unknown, playing the role of the hypotenuse. It says that one side is 7, the other is 3, and this x is unknown, and it wants us to find the answer to 5 decimal places. So let's set this up, right? We would have these two playing the role of our legs A and B, doesn't matter which is which. And then this one is across from the 90-degree angle, meaning it's the hypotenuse. It's going to be alone on this side of the equal sign. It's already almost solved for x. We just have a square there. So let's simplify the right-hand side. When we do that, we have 49 plus 9, that's 58. And when we take the square root of that, it's not going to simplify, right? If we look at 58's factors, we have 2 and 29. 29 is prime, and so there are no pairs. If there's no pairs in our list of prime factors, there's no simplification we can do to this square root. And so we would either have this as our exact answer, well, without this square here, of course, that shouldn't be there. Or if we plug that into a calculator and we find its decimal place, we have 7.615773 and so on. If we want that rounded, we need to look at the 7th place. It's less than 5, and so we keep this number the same, rounding down to 7.61577. Checking our answers, checking our work, we can move on. Question 41 begins a series of quadratic equation questions which do not factor. It is worth, however, trying to factor, and we'll see what it looks like for these not to factor, but essentially these are all going to boil down to using the quadratic equation. I use the AC method with a slight modification that makes this actually equal to the line that came before in the event that it factors. You could put an A, m in each term here and a 1 over a out front to balance. Notice that if we FOIL is still 3m squared, and we only have 2 more spaces left to fill in. There's an extra 3 in here, so we look at 3 times 7 instead of just 7, and that gives us 21. Well, this would require a plus and then a minus here to make the second sign a minus, and that means a difference of 1 for our middle term is what we're looking for in this list of factors, but of course, none of them work, right? That means it doesn't factor. So what else can we do? Well, we can look at the quadratic equation. Making sure that we have this set equal to 0, we identify a, b, and c, the coefficients. This is 3, 1, and minus 3 respectively. The quadratic equation, x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. We plug things in. I think that it's worth evaluating the argument of the radical separately, which is called the discriminant here. 1 squared is 1. The minus times this minus makes it a plus. 3 times 7 is 21. 4 times 21 is 84. And the sum of these two is 85. So this will turn out to be root 85. Does 85 as a radical simplify? It does not. That's because 85 is 5 times 17. Both of these are prime, and without pairs, we have no simplification we can do here. We still have 2 answers, one for the plus and one for the minus, and that's what it looks like when we go to plug in our answers. 1 plus answer, plus right here, and 1 minus. Notice that the negative sign stays attached to the b term. It does not change. You could divide the 6 into each one as well. There's really no problem with that either. Okay, what about 42? So 42 says use any method. It's worth trying to factor, but first we're going to need to set this up properly. In order to go start to factor or to use the quadratic equation, we need to bring this 7 over and write it all on one side of the equal sign, set equal to 0. We could try to set this up using the AC method. We put a 4x in each place and a 1 over 4 out front for balance. We fix our signs. They're all positive here. And then we look at A times C. That's 28. Factors of 28 are 28 and 1, 14 and 2, 7 and 4, and none of them have a sum of 8. That tells us that this polynomial is prime, it does not factor, and we can move on to trying the quadratic equation. I stand by, even in the case where you have a non-monic polynomial, it's easier to use a factoring method than it is to bust out the whole quadratic equation, especially if they ask you to factor it and not solve some equation. Anyway, moving on. A is equal to 4 here, B is 8, and C is 7. And plugging that into the usual formula, we have the following. Now, again, I'm going to evaluate the discriminant. Over here is some scratch work. We have 8 squared minus 4 times 7. That's 64 minus 16 times 7. 16 times 7 is 112. And so this difference turns into negative 48. We're going to need to simplify that, and it's a negative under the radical, and it has squares in its numerical part. So the negative turns into an I that we can pull out, and 48 is actually 16 times 3. That means this turns into 4 radical 3 when we simplify it. It's customary to pull the I to the end, then the radical is in the middle, and then whole numbers are left up front. So when I evaluated the discriminant, it was minus 48. When I simplified that radical, it was 4 radical 3 times I. And now we can distribute this division by 8 into each term. The first term turns into a minus 1. The second term cancels with the 4 or reduces with the 4 to turn into a 1/2. So we have square root of 3 over 2 here times I. Of course, there's a plus and minus that translates into these two answers. As such, you should note that if we ever have a complex answer with this I right here, since it's not going to combine meaningfully with the B in the numerator, we'll always have the complex number here and its conjugate. If they're real numbers for our coefficients and we have a complex root, its conjugate will be another root. All right, let's move on to 43. 43 is another quadratic equation, x squared minus 6x plus 59. But 59 is prime, so this we can really quickly see does not factor. We would need it to be a minus and a minus, so we'd be looking for a sum of 6, but 59's only factors are itself and 1. So we set up our quadratic equation. We have A, B is negative 6, and C is 59. That A was a 1. There's no coefficient appearing in front of this term, which means it's a 1. So plugging those things in, we get the following. I evaluate my discriminant, and I get negative 200. Negative 200 isn't a square, but it's negative, so we can pull an I out. And it's 100 times 2. 100 is a square. I can take the square root of that to get 10 radical 2 times I. So first we reduce the quadratic equation, we fix the discriminant, then we simplify the discriminant, and both of these things can be divided by 2, both the B term here and this constant that we brought out in the course of simplifying the radical term. Dividing both of these by 2, we wind up with the following two complex answers. Note again the number and its conjugate, as we can see. All right, question 44 asks us to find the answers to this equation. But the quickest by far is going to be to use the square root property. We've already got it pretty close to solved. We just need to push it a little bit farther. The square root property says that if I have a number squared, x squared, equal to some constant, if I want both solutions, all the solutions, that's going to require a positive and a negative answer. This symbol stands for two different answers, the positive and negative principal square root of C. And the principal square root for positive numbers is just going to be its positive. The principal square root for positive real numbers is just going to be its positive root. So when I take the square root of both sides here, I get a plus and minus I need to pay attention to, times also the square root of 36. The square root of 36 is 6, so my two equations here should read 7y plus 3 is equal to 6, and 7y plus 3 is equal to negative 6. Subtracting 3 from both sides, dividing by 7, we wind up with 3 over 7 and negative 9 over 7, as shown. Okay, let's go to question 45, 3/4 of the way there. This one isn't going to reduce when we use the square root property, and they say as such. They want the answer given in this form, a plus or minus the square root of b. This is actually a very quick problem. The square root property says we take plus and minus the square root of 7, and that will be our term s minus 9 now. Adding 9 to both sides, we get the answer. This is 9 plus and minus, both of them, two answers, the square root of 17. Yep, okay, on to 46. We have a radical in an equation. We're going to get rid of that by squaring, but squaring can introduce unexpected, untrue solutions into our equation. So we're going to have to check our work and see whether or not it's actually viable. We begin by isolating the square root. We subtract 6 from both sides to get that square root by itself. You can already see there's a problem because we have the square root of something is -1. I don't know if you've ever looked at the graph of the square root of something, but it's not negative. But let's continue. We square both sides, and what do we find? We then get m plus 7 is equal to the square of -1, which is +1. Subtracting 7 from both sides, we wind up with m is equal to -6. And if you're only halfway going through the motions here, you might accidentally put that in as your answer. Be careful on the final exam. They'll put a dangling, seemingly correct answer like this up for grabs. But with any squaring, we're going to have to check our work to see if that's really true. Plugging in -6, I wind up with -6 plus 7 plus 6. Well, -6 plus 7 is 1. The square root of 1 is 1, and 1 plus 6 is 7. But our equation was originally equal to 5. Okay, so when I plug in -6, I don't get 5. I get 7. They're not the same. And so there actually is no solution to this equation. The only potential solution that we found doesn't work. So we got to throw that out. We can't use it. And we note that is indeed what they had as the correct answer. There is no solution, does not exist for this equation. On to 47. 47 is another square root problem. Let's see how this one goes. Notice, though, curiously, they don't have all that blah, blah, blah about no equations persisting there. So let's look at that, okay? So moving the 8 to the other side, we get a positive number, 13. That shouldn't actually put too much of a problem. Squaring both sides, we get 169. If I add 20 to solve for x, I get 189. Now, we could plug that in. If I plug in 189 minus 20, that's 169. The square root of that is 13, and 13 minus 8 is 5. So this answer does work, as noted. All right, now we're into our rational equation problems. We have 8x minus 72 over x squared minus 4x minus 45. They want a numerator and a denominator once this thing is simplified completely. Essentially, the work in all rational equation type problems or rational expression type problems is going to involve factoring the polynomials in the top and bottom of the fraction, and then perhaps using your usual tricks from fractions to simplify. In this case, simplification is all we're doing. If we factor the greatest common factor of 8 out from the top, and we factor the bottom, setting it up with a minus, and then we need a plus. Now factors of 45 with a difference of 4, that's 9 and 5. Then we wind up with two matching minus 9s. They cancel as long as x isn't 9 itself, and we wind up with 8 over x plus 5. Our numerator is 8, our denominator is x plus 5. Problem 49 asks us to, again, simplify this expression completely. In order to do this, we must factor. So we set up parentheses, drop a minus sign down. Minus times a minus will give me this plus. And so we're looking for factors of 21 that sum to be 10. That's 7 and 3. Same thing on the bottom. We put up parentheses. We drop our plus sign straight down. And we say, plus times what is this minus? Well, a minus must go here. Now, because these signs don't match, we know we're looking for a difference of factors that multiply to give me 12 and have a difference of 1. That's 4 and 3. If you do this drop this sign straight down kind of shortcut, you can always put your bigger number there, always. The x minus 3's on the top and bottom cancel, as long as x is not 3 itself, and we wind up with x minus 7 over x plus 4, as noted. Question 50 is a division of two rational expressions. Again, all we're doing is simplifying and then following our usual rules for the arithmetic of fractions. So we begin by factoring. This is difference of two squares, x minus 4x plus 4. This is going to be a plus and then a minus to make the final term a minus. factors of 24 with a difference of 5 are 8 and 3. And on the other side, we have a minus in the first place, and then we need another minus in order to make this FOIL to plus. Then we are looking for a sum because they match. Sum of factors of 32 that give me 12, that's 8 and 4. On the bottom, that's another difference of two squares. So we have w minus 8 and w plus 8 as factors. This means that w minus 8 can cancel in this next term. And moving forward, we then flip this fraction, or what's left, and multiply. Once we flip the fraction, we can see what else cancels. Here we could see a u minus 4 on the top and bottom, as well as an x plus 8. Those two must cancel to 1, and so we just have basically a top and bottom times 1 left over. That's going to be w plus 4 and w minus 3. There we have it. On to 51. 51 is another rational expression. We are asked to multiply these two rational functions. Again, that's going to require that we factor everything. So we take w squared minus 25 and factor it as difference of squares. Then we take a w plus times a w minus, factors of 40 with a difference of 3. That's going to be 8 and 5, biggest one first. Over here, we've got a plus and a minus, again, that we need as our signs. Factors of 16 with a different signs difference of 6, that's 8 and 2. Then we do all pluses, that's plus and a plus. Factors of 50 with a sum of 15, that's going to be 10 and 5 respectively, and we start to cancel. If we have a match on the top and bottom, we can cancel. Here we see the w minus 5s cancels, the w plus 8s, and the w plus 5 cancels as well. Now there's nothing left to do but carry these terms over. There's really no non-trivial multiplication left. It's just 1 times these things. And so we wind up with w minus 2 over w plus 10. There you go. On to 52. 52 is another expression. It's a sort of rational expression in terms of C, not as complicated as the ones we were looking at, but we still have to remember how to add fractions. Remember, that involves getting like bases. We unsimplify this fraction, multiplying by this base on the top and bottom, and this base against its compatriot on the top and bottom. We wind up with 45 over 72 plus 8 times C over 72. Once we have that over 72 part matching, we can simply sum the numerators and get 45 plus AC. There's no reason to try to combine these in any other way. They're not like terms, they don't simplify. This is our final answer, as shown. Okay, let's go on to the next one, 53. 53 is a sum of rational functions. We see that we don't have like bases, so we can't just sum their numerators. We have to get them the same first. In order to get two fractions the same, we can take this denominator and multiply it top and bottom over here. We can take this denominator, x plus 1, and multiply it top and bottom over here. And then we distribute the minus 1 and the minus 5 to get the following. Now we combine like terms to get minus 6x minus 10. And this is over x plus 5 times x minus 1. We could try to factor here, but all we could get out is a 2, and then that's not going to cancel with either an x plus 5 or an x plus 1, so we should really just leave it like this. That's its simplified form. Okay, let's keep moving. So problem 54 is another quotient of rational functions. We can see 6 over x minus 7 over 13 over x minus 7. This one's not going to take much time to do. All we need to do is rewrite this division here as times a reciprocal. Once it's times a reciprocal, we can see that there's actually an x minus 7 in both the top and bottom. They cancel as long as x is not itself 7, and we wind up with 6 over 13. And that is the answer that they got. Okay, here we have a complex fraction. We're looking at 1 over a plus 2 over 7 over 1 over a plus 5 over 7. It's a fraction with expressions involving fractions in the numerator and denominator. To simplify this, we have to carry out the addition that's being prescribed. So if I want to do that, I have to get the bases the same. That means multiplying 1 over a by 7 over 7 and 2 over 7 by a over a. Likewise, on the base, I multiply 1 over a by 3 over 3, and I multiply 5 over 3 by a over a. This completes the process of getting like bases in the numerator and denominator, respectively. Now I can just add in the numerator and add in the denominator their numerators, giving me 7 plus 2a over 7 divided by 3 plus 5a over 7. Notice there's no way of combining these. They're not like terms. Now we take that division and rewrite it as multiplication times a reciprocal. The A's are alone the things that cancel and match in the top and bottom, and distributing the 3 and distributing the 7, we get the following. Except for the order of addition, which doesn't matter, we can see that's what they got in the answer key, and we move on to the next business. So we're now on word problems. We have a discount problem here. You're almost guaranteed to see one of these on the final exam. It says Joyce paid $12.50 for an item at a store that was 75% off the original price. What was the original price? To do this, we just have to understand what they mean by 75% off. They mean that the amount that you paid, the amount it was on sale for, is the original price minus 75% of the original price. A percentage is a fraction of means times the original. 75% is the decimal 0.75 or the fraction 3/4 if that's your fancy. Then you can take the difference here, x minus 0.75x. Well, 1x minus 0.75 is 0.25 or 1/4. And dividing by that on both sides will take and give a 50 from this 12.5 divided by 0.25. That's 50.00 if you want it rounded to the cent. So if you paid $50 for something originally, but then they got rid of 75% of the price, the new price would be $12.50. A TV went on 5% off sale. The sale price was given as $237.5. What was the original price? This is precisely the same problem with different numbers. We have a sale price, a price paid, which is equal to the original price minus the percentage you took off. Now that's going to be 0.05 for 5%, which minus from 1 gives me 0.95 times x. Dividing by 0.95 on both sides, 237.5 divided by 0.95 gives me 250. 250 is the answer. We move on to the next one. Now you have a slightly spicier problem. This one says the admission fee at an amusement park is $1.5 for children and $4 for adults. On a certain day, 294 people entered the park, and the admissions fees collected totaled $916. How many separately, children and adults, were admitted? You want to figure out both the amount of children and the amount of adults. To do this, we have to take advantage of the fact that we've been given two items of information here. We've been given the total number of people in the park. We've been given the total amount of money collected from those people. That lets us set up two facts. Let's call the number of children C and the number of adults A. Then the amount of money we're going to collect from adults is $4 times A, the number of adults. Likewise, the total amount of money coming from children is 1.5 times C, the number of children. Now, the total number of people is A plus C. We were told that's 294. The total amount of money is going to be the money from adults plus the money from children, which was 916. In order to solve two linear equations with two variables, we can do the following. We could solve for one of the variables. It's probably easiest to do right here, just minus A or minus C over to the other side. Then we substitute that expression into this second equation. We have C given by 294 minus A, so I replace this C with that expression. That gives me 4A plus 1.5 times the quantity 294 minus A is equal to 916. Now we just have one equation with one variable in it, which we know how to solve. Distributing my 1.5, I get 1.5 times 294 and 1.5 times A, the minus sign between them. Now we can combine like terms. 4 minus 1.5 is going to be 2.5, and 1.5 times 294 is 441. To solve this for A, we keep pushing. We subtract 441 from both sides. From 916, that gives me 475. And to finally get A by itself, we want to just divide by 2.5. If I divide by 2.5 on each side, I get this whole number, which is a good sign we're doing this right. A is equal to 190. Now that we have one variable, it's easy to go back to our equation that we solved for C and just plug that number in, which gives us 294 minus 190, which is 104, our number of children. So for adults, we got 190. For children, we got 104 as shown, okay? Problem number 59 asks us to graph this linear inequality. This is going to require us to use our knowledge of graphing lines, and we will use a test point to decide what side of the line should be shaded. First, graphing the line. We should use a dotted line for this one because we have strict inequality. So the line itself is not going to be included, but we still want to depict it, so we use a dotted line for that. Then we can use the fact that this is in slope-intercept form. We have a slope of 1, a y-intercept of 3. So we start at 3, and we go over 1, up 1, and that gives me a point. So this is our line. It cuts the plane into two parts, something over here and something over here. We're going to shade all of the points on one half or the other because we want x's and y's that satisfy this inequality, and it's going to be something on either side of this plane or either side of this line, which is our edge case. To see which side we should shade, we pick a test point. It must be a point that's not on the line. But if the origin 0, 0 is available, that's usually the easiest one. As long as that is not on the line, we can use it as a test point. Now, plugging in 0 and 0 for x and y, I get the expression 0 is less than 3. 0 is less than 3. And so that means the test point satisfies the inequality. And so will every other point on this side of our first line. So we shade all of those points. And as you can see here, this is exactly what they got for the correct answer. We have the line going through 3 with slope of 1, and the side including 0, 0 is shaded. Any point on here, any of these x and y pairs that you plug into y less than x plus 3 is going to work, is going to satisfy that inequality. All right, we have one final problem. This is problem 60. We want to graph this, and we want to shade on the appropriate side. So let's begin by putting it in slope-intercept form. That will make it easier to graph. We subtract 2x from both sides and divide by -8. Now, dividing by -8 is important that we recognize that this is a negative because we're going to have to flip the direction of the inequality. It goes from being a greater or equal than symbol to a less than or equal to symbol. Now we have a slope of 1/4 and a y-intercept of -2. So we put a dot at -2, and then we go right 4, up 1. 1, 2, 3, 4, up 1. There's our second point. And we're going to use a solid line for this because this is a not strict inequality, an inclusive inequality, one that includes the edge case of y equals 1/4 x minus 2, which is this line. So to show that, we use a solid line, and we're still going to use test points. Now, 0, 0 isn't on the line, so let's plug it in. If I replace x and y with zeros, what do I get? I get the statement 0 is less than or equal to -2. That's not true. That's a false statement. -2 is the smaller. And so we would not shade to include 0, 0. We would shade to exclude it. We would shade on the other side from our test point since we got a false statement when we plugged it in. That's this lower half here. Checking our answer, that does appear to be the case. We have the points -2, 0, and -1, 4. It's a solid line, and we're shading underneath it away from 0, 0. One other way we could have proceeded to graph something like this, since it's already in this really nice standard form, we could have plugged in 0 for y and divided by 2 to get the x-intercept, plugged in 0 for x and divided by -8 to get the y-intercept, and still used our test point right here. Would have been real easy to plug in and get 0 is greater than 16. That's, of course, false, and so we would shade away from the origin. All right, that concludes the review. Thank you very much for your patience, and have a great day. Good luck with your studies. I'll see you in the next class.